from you. And it's my great pleasure to introduce today our speaker, who is Yuichiro Mori from AIST in Japan. And Yuichiro will speak about a proposal of expressive quantum supervised machine learning with Kerr-nonlinear cavities. So Mori-san, over to you.
Thank you. Introduction. I'm Mori. I talk about the title. This is based on the accepted paper. Okay. So background is in NISQ computing, near-term computer, we can use limited number of qubits and operations. So there are some noises, and so if we perform many times operations, then noise causes errors. So limited numbers of operations. And so in near-term quantum computing, hardware efficiency is very important. And then, so machine learning is one of the most outstanding applications of variational quantum algorithms, which is attention to the near-term computing algorithm. And so we call VQML as the machine learning based on the idea of VQA in this presentation. Okay, so now we propose idea to perform supervised machine learning, and so we use the curve fitting problem as an example. So I introduce the curve fitting problem at first. And curve fitting problem is when we have n data. This is called teacher, and we have a model with a number which is a function with a number of parameters like this, and adjusting the parameters, and we depict the curve, and we fit this teacher data by adjusting the parameter. Okay, so in variational quantum algorithms, we perform the problem. VQA is a classical and quantum hybrid algorithm. So in one side, classical idea, and quantum side is a experimental machine. So, and then if we want to perform machine learning, then we have classical data and quantum state, and encode the variable x by using a unitary operator, and encode this theta parameter as by unitary operator, and with the parameter theta. And finally, we can perform some measurement, and we evaluate cost function like this. And to minimize the cost function, we perform a classical algorithm, and we revise the parameter theta and perform the experiment and minimize the cost function, then we obtain a result. So machine learning is very qubit-based machine learning is very attractive, but in terms of expressibility, this is limited because dimension is limited and possible interaction is also limited. So expressibility in qubit-based variational quantum machine learning is very limited. But to solve the problem, data reuploading idea is developed, but this means we need another operation, so depth becomes larger. This is not so good. But this problem may be avoided in bosonic system because bosonic system has an infinitely large Hilbert space, and we can different operation from this the qubit-based idea. So we consider variational quantum machine learning, but based on bosonic system. And recently, Kerr-nonlinearity, Kerr-nonlinear cavity is very attractive to Kerr-nonlinearity can be exploited on the superconducting quantum circuit, and this is useful to make Kerr-cat qubits and other quantum annealing or some other applications considered. And in the experiment, parameters detuning, power of parametric driving, and coherent drive are adjustable. So we consider these parameters as parameter theta in this unitary operator. So then we let's show the idea of the parametric quantum circuit in our case. Then prepare the coherent state for the initial state and encode the variable x by using this unitary operator and this simple Hamiltonian. And the duration t is fixed. Third step is we adjust the parameter delta PR like this, and we use this Hamiltonian as to make this unitary operator. And in this case, there are only 3 parameters, but in the actual variational machine learning, we need more and more parameters. Then we change these parameters, and we repeat these operation. So last we perform measurement, and the expectation value of A plus A daga in our case is considered as a model function. So now we show our results of our simulation. We compare our scheme. This is composed of one mode bosonic system and 36 parameters. This means 12 layers we use. And metalize conventional qubit-based scheme. This is 6 qubits and 2 layers. This number is chosen for dimension is 64 and the number of parameters theta is same as 36. So we choose the parameter. And we perform the data, perform the curve fitting with using 100 teacher data generated by a Gaussian absolute function, square wave, and this artificial function. This is a result, and blue dot is teacher data, and orange curve is model function obtained by the simulation in our proposal. And green is a conventional qubit-based scheme. And these values are the final cost function. And these are numbers of iterations. According to this, as we can see, our model is more expressive in all cases. And the second result is our scheme is adjustable or in terms of the expressibility. So if the initial state alpha is ket 0 or number eigenstates, then we can't encode x. So expressibility becomes 0. But so in non-zero alpha, then expressibility is not zero. So we consider the initial alpha relates to the expressibility. And this question, the answer is yes. This is the result. And the first alpha is 1, then the orange dotted curve, and the right side is Fourier transform of the left result. In both cases, alpha 1, 3, 5 cases are plotted. And in alpha is 1 case, expressibility is limited, and this curve is near to the qubit-based case, but in alpha is 5 case, very oscillating, result seen. And this means that in small alpha case, overfitting problem can be mitigated or not. So I check the whether overfitting problem is mitigated or not. So this is the result. We only use 10 teacher data. Then when alpha is 1, the curve is this red curve. But alpha is 3 case. This is highly oscillate, and this is overfitting problem is caused. So so I so sorry, alpha, small alpha. So the size of the alpha can adjust the expressibility and overfitting problem avoid the size of the alpha can be used to avoid the overfitting problem. So okay, and the expressibility of our bosonic scheme is caused by a large dimension of the Hilbert space, and so in our cases, higher excited states should be used. But higher excited states are weak against decoherence. So we want to reduce the higher excited states in some cases. So we considered whether utilizing 2 modes could lead to suppression of excitation states or not. So this is the result, and the left result are the simulation using 1 KPO is green dotted curve, and 2 mode cases this orange curve. And in both curves, the expressibility is almost equal in these cases, and the photon number, which means average average number of the excited states, and in 1 mode case, 10 or 12 photons are used. But in 2 mode cases, we only use 1 to 3, less than 4 photons are used. So the photon number can be reduced. Okay, so this is the conclusion. Our bosonic scheme with Kerr-nonlinearity can be more expressive than the conventional 6-qubit case with only 1 mode. And the expressibility is adjustable with altering the amplitude alpha of the initial coherent state. And increasing the number of modes, we can suppress the higher excitation without reducing the expressibility. Thank you for listening.
Excellent. Thank you very much, Yuichiro. Lots of interesting things and plenty of time for discussion. So I'll open this up if anybody has some questions for Yuichiro. Tadashi Kanawaki has a question.
Thank you for your presentation and congratulations on the acceptance of the quantum machine learning
Thank you.
machine intelligence.
Yes.
So my question is, could you define the expressibility? So if you can
this is a
quantize this concept
problem.
that help us.
So the cost function for any function, if the expressibility is high, for any function, we can reduce the value of the cost function. So I consider only the value of the cost function, and so this means that there are possibility of the our scheme is only to use this limited function. This possibility is not denied, but this artificial function or the specific point, the curve is very well fitted. So we believe that our scheme has large high expressibility.
So you mentioned that the changing the alpha. So you believe something you still do not define the expressibility, but you can control your expressibility. So if so you can define clearly, that may help to understand the nature of the
okay. So this we refer to the this paper, and in this paper, the expressibility is discussed with using the Fourier transform of the output function. So if there are many peaks on the Fourier spectrum, then we can obtain the high expressibility in their discussion. So
it's something related to the bandwidth, frequency space. So the high expressibility had something that can represent the highly changing functions. Correct?
Yeah. Highly oscillating function. Then large number n, and then the you
understood.
can consider the if you expand the function, then there are many spectrums. If the alpha is larger.
Now I get some idea of the expressibility. Thank you.
Yeah.
Any other questions for Yuichiro? Maybe I have a question. So you had a nice comparison of your parametric oscillator technique by comparison with conventional technique due to meter-i.
Yeah, thank
and
you.
you very carefully made sure that the number of free parameters was the same in both cases, which is good. And I guess you had 36 free parameters.
Uh-huh.
The number of layers was
Uh-huh.
different in the two cases. So I think
this is an important question. So surely the layer or the number of layers is larger than the qubit-based case, but in our scheme, we very simple operation can be applied to the system because the parameters are defined on the Hamiltonian, and so so in our scheme, we consider our scheme is stronger than the conventional qubit-based scheme because the operation is complicated in this is depends on the how to make the how to implement the qubit, but our scheme is simply defined. So I consider our idea is stronger than the increasing number of depths in some extent.
So I mean, I agree with you, but let me just make sure that I have understood. Do you need a much longer coherence lifetime of your qubits
this is
than you would do with the conventional technique, which requires only 2 layers?
Yeah, this is exactly true. Yeah.
Okay.
Coherence time is needed. Yeah.
Right. Okay. So maybe the next question then is it possible to construct a fair comparison between your technique and the conventional technique using a similar number of layers and similar number of free parameters? Maybe that's not possible.
So please once more.
This comparison means that you need more coherent qubits. And in some sense, that's not a fair comparison between the two methods. So is it possible a comparison where you have the same number of layers in the parametric oscillator approach and the
this is partially true, but in our case, only we use one mode, but if we compare the coherence time or the coherent nature, then we should be the same number of modes and qubit because this meteorized qubit-based scheme is one qubit is prepared by one mode. So this is not the fair comparison. Yeah.
Good. Yes, I'm beginning to understand. Thank you. Thank you. Are there any other questions for Yuichiro Mori? If not, let's thank the speaker again. Thank you very much for your interesting presentation. A round of applause from me on behalf of all attendees. I look forward to seeing everyone at next week's seminar in 7 days' time. Thank you very much, everyone. Bye-bye.
Bye. Thank you very much.
Yeah.